So in this lecture we will discuss about GMM as a classifier model, and we will be using Python programming to implement the things. So we are, as you can see, that it is Visual Studio Code IDE, and we are using Python 3.6.9 version. So this is the working directory. Let me create a file first. Classification.py. So now we just importing some of the functions. Let's say do something sys model to exit from the program. Scalar learn set is from import mixture. Yes, this mixture then matplotlib by plot import PNP one we want to externals import job to store the models. So these are the necessary modules. System, that is a sys numpy. From the scikit-learn we are importing mixture matplotlib for plotting the data, and scikit-learn external. From there we are importing joblibs to storing the models. So first we'll be creating generate data. We'll be generating generating the data for training the models. Let's say another function we can define, that is basically train GMMs. Okay, so we can define that for creating, let's say which will prepare the model. This is the main function, and this is the entry point. So just all the main functions. Let's see, class just these things and correct. So we will be defining this particular data generation function model. This is particular method or the functions which we are creating generate data. Let's say that we wish to generate data from a Gaussian distributions. So we need to specify mean and standard deviations and count how many samples we want basically, and we will do some checking that what is the length of these two lists, mean and standard deviations. So if the lengths of these two are 1 and 1, then that means we want to generate a one-dimensional data of a specific mean and associated standard deviation. But now the situation may be somewhat different. and the user can provide multiple user can provide data mean as a list, standard deviation as a list as well, where this can have any length, this can also have any length, but if the length of these two lists are more than one, the length must be equal. The condition is that I want to set. So length data mean, if it is greater than 1, STT is also greater than 1. If the length of these two individual lists are more than 1, they must be equal. If it is not, there is a problem. So just adding another condition, length data mean is not equals to STT, then the problem. So what is the problem? Mean and STD must be same length, and then system exit, right? It will come out from the program. Now okay, this is fine. Now what do you want to do? Let's say the condition is somewhat different. If what we are assuming that the length of data mean is more than data standard deviation, suppose the length of this two, okay, that's fine. If these both of them individual more than that, and if they are not equal to that, okay. So now the condition is that we said that if, okay, let's check it. If length data mean equals to 1, this is 1, and data steady, data steady is 1, correct. So now data mean equals to 1, that means user providing single main list with one element, data steady list of multiple elements. Here is the situation. What happened in that condition? So what we're doing, basically we are capturing data mean is to 1. That means data mean only one element, and we will define data mean as string. Okay, so what we're doing, suppose the situation is that mean is a list of only one element, and 2,3. So it satisfies this condition, and in that situation we will pick up this value of mean which was provided 1.2 inside the val. Now val will be copied in this particular list element, and then the same value will be repeated as many number of standard deviations. So output is basically unit plus 2 equal to 2 std plus 2 comma 3. So this is the output. Okay, so now if we want to do the reverse thing, that means opposite one, data means 1 sticky plus 2 value plus 2 vector. So if it is done, then now we want to capture the dimension. Dimension is basically maximum of the two elements. But the first element, one of the element is determine. Sorry. Dimensions, and now we are just printing. We're getting confirmation message. Selected dimension, comma 2. Okay. So now we are basically preparing the data. Let's say data equals to zeros should be off. So we want to generate a data of a structure where there are multiple rows and multiple columns. So number of columns is exactly number of columns is basically equals to the dimension, and the number of rows and the count values which are already been provided in the function input argument. So row comma columns is true. So it will be derived over the dimensions, and is to random. It's coming from a normal distribution. Determine ith determine ith mean value, ith standard deviation, single dimension. So once it is done, return data. This is the end of the program. So okay, so the result standardly different functions. Okay, so if we just write, just we check this is said before, let's say this is 1.2 problem. So what the things you are doing basically here, okay, capture it to explorable. Let's get did this right. Okay, so data dimension 2 and 100 samples are 2 dimensions. It is working fine. Now if it just 1 comma 2, then also dimensional data it returns 100 by 2 if it is this thing, 200 by 2 if it is, there should be error. This mean and standard deviation must be same length. So that's what we do. Fine. So data generation is completed. Now it will be just model, something like that. Let's say that we are going to create the model. So if you want to do that, what I need basically the data. We need basically data, number of components and the data basically. Data set and number of component. Now after that we'll be creating a model. Dot this function mixture, and you can see n underscore components to then plus p plus it through, and then let's say that true, so that we want to print the message of it. Now we have to fit. Over the data. Now our task is to return the model. It's done. So we created the model and this one. Okay. Into the main function we are creating, let's say n plus 2 500 samples we would like to create. Pass one data, we would like to create plus one data. So we created, let's say one patch of data is basically data set, generate data, and we wish to create from the bin distribution, let's say 1 comma 2, and then standard deviation distribution 0.2, let's say, and let it be 1.2, no problem, and number of samples. So if you just click on, that is it requires data mean, that is 1 comma 2, it requires standard deviation, and okay, fine. So it returns a data class 1 dataset. So we are taking inside a class 1 variable the generated dataset. Now we is generating second batch of data for class 1, as if class 1 data is composed of multiple Gaussians. Let this be 0. So we are choosing different mean values. Let it be 0.5, 0.7 values. Class 1. So it is basically class 1 data, so we can concatenate this particular data class 1 comma data set, and what do you want, basically the axis, because we want that okay, so number of samples are being appended in rows, and both the dataset had the same number of columns, so we can get axis equals to 0, row wise appending. So you can see why we are using number ANP concatenate, because dataset which was returned by this generate data, that was basically numpy array. So that's why class 1 is also numpy array, so we use numpy concatenate function. So now let's suppose now using that same thing of class 2 channel. Let's say that I'm just taking a shift. Let it be 0.3. This was didn't change a bit. Class 2 data and second batch minus 2.5, that is it is shifted, and this is 1. So let it be change 1.2. So now we are creating the model. Model for class 1. What would be basically equals to, what is that? What to be CR. So find it. What it requires data. Class 1 data, number of components, set is equals to 2. Also we are getting back to two Gaussian components. Now we want to set the models using joblib.dump. Joblib.dump. Now the model we want to set G1. Let's say the file name is class 1. You can give extension as well. Let's GMM. let's sorry, activity model, so that we can restore it. We want to restore back job lead. Load the file name used, this one, the file name used like that. So we are restoring these models. So now classify. See. So now we have to classify these things. Correct. So that's for that case we are creating a sample point. Let's say the sample point we are creating by using numpy array. So we run numpy random. Normalized random values of size 1, 2, 1 row, 2 columns. So multiply by 2, multiply by 3, multiply by 4, whatever you can do exactly for shifting the value to our different standard deviation. Now we will be just taking class 1 score. What is that class 1 score? It is basically log likelihood. It's the model. Let's go early. So let me just run this code first. So now this is good. This is working fine. Selected your initial tree. So 4 batches were created. Initialize converts true. Initialize the zeros converts true. That is 2 model we created. That's why this is good now. So now we want to get the prediction for class 1. Score samples. It should be samples, okay? Score samples. Sample point. Let me run this code. Yes, it executes. Class 1. These two colors. So these are likelihoods. So it is more likely to class 1. Now what to do, basically we have to just plot. Let's say that we want to get the score. log likelihood for the training data. Log that we are naming the log class 1 plus 2. Samples for class 1 data. Class 2 from model 2. Log class 1 model 1, let's say. That means this is I'm calculating log likelihood for class 1 data from model number 1. Now what I'm trying to do, log class 1 data from model 2, log likelihood of class 1 data from model 2 GMM. So let's put class 2 plus 2, it is from say class 2 from model 1, class 2 from model 2. That's true. Now clustering application, it is different application, we will not show it here. Now let's see, it is the time for plotting. Okay, how many figures do I plot? Basically is that left panel we want to plot the data. So let's say its size, let it be 12,5, it bigger one. Its pay, we are using first pay. 2 by 2, 2 row 2 columns. So let's say we want a big screen where left side, first row first column, second row first column will occupy for data plotting. Okay, so this is x1 fig dot add subplot. Let's pick both the row first column. And this is axis 2 over the screen, first rows second column for one thing, and for axis 2 and axis 3 will be using second row second column. Axis 3 second column. Axis 3 is that. Scatter plot class 1 data, class 1 data, all the rows first column, all the rows second columns, and we wish to use let's say that marker, as a marker we wish to use marker style, let's say general, let's say line with one. And second class data marker round shape. I think it's better. One is okay for us. Also in the plotting sample data. Sample point. Let's see the square box. I will integrate so that it is uniquely identified. Let me plot it. Let me plot it first. If we do that, +1 +2 sample point. If we run this code first, see what happened. Yes, this is okay. The point is far away from here. If we run it once again back, it is too closer, so you can see. Okay, so now we have to see what basically the class prediction comes from the GMM model for this green point, sample point. So what you can do, basically predict a class for that. In that particular case, predicted class, number of zeros, where is the sample point. Class ones. Class ones. Predicted. Plus, let's say 1 is plus 2. So now we just come down, and if we wish to add some text to this particular title, subtitle, we just write it down. Predicted class. Should print the title section. Predicted class. Okay, just let me predicted class. Okay, this should be class 1. Okay, fine, this is the class 1. Let me run once again class 5. Okay, class 5. It is a class 1, it is more closer to class 1. It is class 1 still. Well, so we are intentionally making this as a -3 plus 2. Let's see what happens exactly. -3 plus 2, and it's done. reshape one local projects, because we prepared the model with a data of dimension 2, but if we don't reshape it, it returns basically one dimensional data, so that would produce an error. This is print class 2. Let's go. It is working fine. Looks nice. It's let me do some decoration. It's later. Let's say it is dimension 2 of the vectors. Let's see how it appears. It appears good. Here we wish to plot class 1 data log load from two different models and the mixed of a cluster data. So what we will do is to plot class 1 model 1, and this is, let's say, class 1 model 1 data. Let the line weight be custom line weight is 1 Osh Control C, just putting the grid lines. Do this, how it appears. It's good. You have to name log likelihood here. Class data 1 model 1 prediction, which log likelihood values are blues, and these are these. So now probabilities. I think this is okay. Same thing will be using for access tree. Just the key changes. Class 2. Class 2 probabilities. Let's see how it appears. Yes, class 2 from model 1 log values are less, whereas class 2 model 2 log values are more. That's true, that's expected to be. Now we want to make it little better. Right layout, some other figure looks nice. Takes a nice spacing, automatic spacing, is good enough. So it's true that for class 1 we use this dataset as a training data, and the associated log likelihood values are that which are more than this class 2 data, and this is model 2 log likelihood prediction, where model 2 data were prepared by this class 2 data. So the log likelihood of this particular class data associated to log model 2 is higher than class 1 data. That's it.